So, bound imports. So we said that on disk, the import address table points at that same data structure as the import names do. In memory, it gets flipped around and points out to other DLLs and things like that. Bound imports are basically pre-filling in that import address table so that it points out to wherever at compile time you think those addresses would have pointed. So basically, the compiler goes around and says, okay, and notepad.exe, you are going to import from kernel 32. Well, kernel 32 is asking for this base address, and it's saying that the function is at this offset. So I think that at load time, you're going to get this absolute virtual address. I'm just going to go ahead and put that into your import address table. If it's wrong, all right, whatever, the OS will fix it up after the fact. But if it's right, then you've got some speed optimization that the OS didn't have to go search an export table for a string printf. So bound imports or binding is basically just pre-filling in the import address table with the absolute virtual addresses that you assume that a particular entry will have at runtime. So basically, the linker does the same job as an OS loader would have done by like running around and looking who you're exporting from and just filling in the table. So now we already saw this. This was the image import descriptor. We're going to use the same data structure again. We're going to care about the same fields again. But the only difference here is that whereas previously there was a time date stamp and like I just said, we don't even care about it. It was actually 0 last time. If you go back and look at your import descriptors, you'll see the time date stamp was always 0, so there was no real time stamp there. Here, it's -1. So again, there's no real value there. So we're going to say the same data structure, but this table is going to be separate from that other table. So bound imports table is going to be off to the side, separate from the regular normal imports table. All right, so back to the data directory. Looks like index 11, given that IAT is index 12. There's going to be a separate data directory entry, which is going to point you at a separate bound import array of these things, right? One per DLL. And the intent for this, basically, yeah. Okay, yeah, sorry, I just misdescribed that a little bit. So, sorry. This data structure is not actually going to be used for the bound imports array. There's going to be an array, but it's going to be different than this. This is just how we slightly change the regular imports, normal imports descriptor table or directory table, whatever. Whereas in the normal imports, this time date stamp is going to be 0 in order to say, basically, if it's 0, it's saying I use normal imports, and my import address table is not pre-filled in. If it's got -1, it's saying to the OS loader, my import address table is going to be filled in. You need to go, check against this other table to determine whether it's filled in with accurate information. And this next table is going to be all about, how we determine whether something's accurate or not. Basically, what we're going to be notionally going towards is you pre-fill in this table, but you got to put some information off to the side saying what version of the DLLs it was that you bound against. Because obviously they can get out of date, right? You can say, at the time I compiled my application, we had this version of kernel 32.dll, and printf was at offset 2000. Printf isn't actually in it, but bear with me. We'll say msvcr 100.dll. And we bound against msvcr 100.dll. Printf was at hex 2000. Now there's an update for msvcr 100.dll, and now printf is at 2020 or something like that. Everybody who compiled and bound against that thing, their pre-filled in entries will be wrong, right? And so what you want to do is when you pre-fill in entries, you want to say, look, this is correct if you still have the same version of msvcr 100.dll on your system. So the OS loader is going to use this next table to figure out if it's still got the right version. Because if it just can see right off the bat, I don't even have the same version as you bound against, then it knows it just has to do the same process as we talked about before for doing imports. But if it sees it's still got the same version, then it can just go ahead and trust that these pre-filled in entries are correct. All right, so this table points at a different type of data structure And that data structure, we're only going to care about one thing, and that's a time date stamp. This is the time date stamp basically specifying the version of the DLL that you bound against. I don't know why, I mean, I should put the screen here then. Offset module name, I guess we kind of care about it. I kind of don't. It's just it's the offset to the name that's associated for this particular DLL. Because we're going to have a list of these data structures, which one per DLL again, for each thing that you bound against. That's not the same color, but whatever. All right. So we have in a P view, sort of view of things, it will show you a different data structure. It'll call it the bound import directory table. So whereas the quote normal import directory table is just the import directory table, there's a separate bound import directory table. It's got three things. Like I said, we only care about the time date stamp really. It's saying, you know, here's the version that I bound against, and then, you know, we care about the name, I guess, to the degree that we need to know what name goes with what version. All this is a big array saying, look, I pre-filled in all your COMDLG32 imports, but I pre-filled them in from a COMDLG that had this time date stamp in its headers. I'd love to tell you that that time date stamp came from the one that you already learned about, but it actually comes from the export address table. But there's some version number associated with the file, and it's putting that version number in right here and saying, I used COMDLG that had a time date stamp of that. I used shell32 that had a time date stamp of that. If the OS is loading this thing up and it's saying, oh, I see you use bound imports. Let me go check if I have that version. Yep, yep, yep. Oh, that com control 32.dll, I have a different time date stamp in my com control 32.dll. So I know I shouldn't believe your pre-filled in entries, and I'm just going to go fill those in the normal way that I do with every other import entry. So, and I'm trying to ignore this for now, but later on when we talk about exports, we'll pretty much come back to that there are some cases where there's an extra data structure. I think actually I end up having to tell you about this anyways so that you can answer the questions. But since I want to get you to break, I will come back to that. Yeah, see, teaching to the test. I know, sorry, I gotta tell you about it before we leave. And then I'll remind you when you get back. In this round, we will have questions to the effect of how many, bound, we'll basically be saying, how many bound import descriptor entries are there? Or, no, we'll say, how many bound import, image bound import descriptor entries are there in this particular binary? So basically, they look exactly the same, but it turns out we interpret these values differently if they have a 0 as this last field, or they have a non-zero last field. So this is basically a structure that is mixed together. And so everything that has a 0 at the last entry, we're going to call an image-bound import descriptor. We're interpreting it as that data structure. But once you have a 1, it's still a bound import descriptor, but then the next thing immediately after it, there will be one data structure immediately after it of the exact same size, but we interpret that as an image-bound forwarder ref structure. So the only reason I tell you this, the only reason I'm forced to tell you this for this particular round in the quiz is, if I say, how many image-bound import descriptors are in this, or if I say how many bound imports are in this thing, what I want is all of these entries except, you could count all these up and subtract, 1, or if there were a 1 and a 1 here, you'd subtract 2. But the point is just whenever you see some non-zero entry, you're going to see that many other data structures immediately in line after it, and then we now continue on. So we see one other thing, and then we continue on with the things we care about. So if I asked you on this thing, how many bound import descriptors do we have? How many do you think we have?
Nine.
6, correct. I believe it's 9 from last time. 1, 2, 3, 4, 5, 6, 7. This is still it. This is not it. 8, 9. right? And we're going to not ever count these null entries. So this really only matters for what.
Please clarify.
Yeah.
Question. If
No, I mean, you got the question right. So what should I clarify?
okay, the number that you have marked there says 1. If that said 2, would the right answer be 8?
Yes, basically. Although if it said 2, this entry down here would say reserved like this entry was. I mean, that's the little tiny tip off that this is something else, right? Everybody else says number of forwarder modules. It's interpreting it that way. This one says reserved because when it is one of these forwarder ref things, like the last field is never used, and so it's reserved. But yes, you're correct that if it said 2, this would be 8, and this would just be slightly different. Yes.
So you have to have at least one bound import descriptor before you can have any of these forwarded ones,
Yes,
right?
yes, exactly. You'd never be able to have any of these forwarder things unless you were binding against at least one thing to reference that we've got some.
So it actually is related to the thing above it.
Exactly, and that's
Okay.
what we'll see when we get to exports. This NTDLL is in some way related to the kernel 32 as far as binding and imports and exports is determined. When we get to exports, I'll show you the sort of weird case that there's this, well, just to skip ahead and just tell you right straight away. There's a place where kernel 32 has a function that says, I export this function. And you go to try to import it, it says, oh, actually, that's an NTDLL.dll. And so that's called a forwarded export. And so this is just trying to kind of keep track of that information because for binding purposes, if you find out that your kernel 32 is out of date, that could have implications if you were importing something from NTDLL secretly. You know, that may or may not be out of date. But as far as we're concerned for teaching to the test, I may ask you questions, and you just need to basically, subtract out the sum of however many non-zero entries there are. And again, big picture, the only point of this data structure is to tell the OS loader whether or not pre-filled in import address table entries are probably invalid or probably valid. Okay. Saying as long as you've got this version, where a version just is given by a time date stamp, then your entries are probably good.
Quick question.
Yes?
So these are all, seems like just time optimizations in terms of loading, right? So,
Yep.
I mean, I guess it must be significant or else they wouldn't do it, but it doesn't seem like it really should be. So why did they do it?
Well, I think it is, I mean, it depends on your determination of what's significant, right? So what I'll say is that I don't think it's significant anymore, and what I'm really curious, my question is why do they still do this on Windows 7? Because this has to do with like assuming that the base address is whatever the base address, it's assuming that, kernel 32 will be loaded at the base address in its headers. So it'll be at that image base. We've got ALSR, and we know these DLLs are going to be moving all over the place. So if kernel 32 gets loaded at this location, all those pre-filled in entries are wrong based on the assumptions, and so they would have to be fixed up. So, yeah, but it's apparently enough of a speed hack that Microsoft thinks it's worth keeping around and worth doing. So all I can say is they certainly do their performance testing, and they must have found it to be relevant. All right, so this is, again, we had just seen that interpretation of, this data structure for normal imports. We said IAT, name, stuff we don't care about. Well, that time date step that we didn't care about before that should have always been 0 is now Fs. This is kind of telling you there's going to be some bound imports going on. But the real authoritative source of the fact that there's bound imports is you go to the data directory, and that bound import entry has a non-zero RVA. That's saying, like, look, there's a pointer to a data structure for bound imports. Use that information. But this is sort of the normal entry. And here is advanced API 32. And the key point is that these entries for the actual IAT entries are pre-filled in with real addresses. You can see these are more like absolute virtual addresses within the user space. And so these are pre-filled in instead of RVAs. And this is just it would be good to show, yeah, the problem is basically since PView doesn't do 64-bit, I can't show you that, but I can show you for 32-bit.
I'll show you those are bound.
Say again?
How do you know those are bound imports?
How do I know those are bound imports? Partially just because, So it's again kind of weird. So the right way to do this, let's just look at this in the real thing so I can move around. CFF Explorer, open up Notepad. And I move over to the new tab. That's very important. Import directory. It's got Fs that are -1s. I said back here. The time date stamp is -1 if bound. So it's saying it's bound import. But I have to have like a compilation. It's like, Corey especially drops his pointer all the time. I want to like have a clip show where it's just like the pointer's dropping continuously. It's having like 5 minutes worth of password right now. But the real authoritative way that I know that these are, bound imports and that's a pre-filled in sort of import address table entry is because I go to the data directory, I go to index, whatever this is, 11, and this is non-zero. Now, this is just a bug in CFF Explorer. It is within, oh, no, it's actually not. This RVA is not actually within any section. It actually, it turns out, this particular bound entry, it's putting it after the section headers, but before the first section. So it's think like optional header, section headers, and then it turns out they put the data structure for the bound imports like right there after the section headers. And then like here's the data for the .text section later on. So it's actually kind of interesting that that just happens the way that they bound it. But we know that it's using bound imports because it's got a non-zero bound import RVA telling us that if we go to 2E0, we will see the data structure for bound imports. And this doesn't actually parse bound imports, therefore I have to like kind of do it the manual way, 2E0. So, E0. So now I would interpret these as like time date stamp, RVA to file name, and then number of forwarder refs. Time date stamp, RVA to file name, number of forwarder refs. This one actually has more things that have forwarder refs than the other one. I'm parsing this right. Let's see that in PE view. Let's go to Notepad. See, this is why I couldn't just open up Notepad before when I was trying to talk about normal imports, because I know that Notepad uses bound imports. Right. Since it's 64-bit, you can't look at it. So this, like I said, is start getting into trouble here with 32-bit in PE view will do it. Let me think if I don't have Process Explorer on here, so I can't really show that. Yeah. All right, so it's pretty much going to be CFF Explorer. Well, yeah, for 64-bit, you basically have to use CFF Explorer. And if I ask you what the RVA of a particular thing is, this is actually an AVA. So I hopefully don't ask you what the RVA is, because then you'd have to go up and find kernel 32, and then you'd have to get its base address and subtract that off. So hopefully I'm just asking you what's the virtual address of a particular entry in this round. All right, well that's the easy extra import thing. Let's take a 5-minute break, and then let's go on to the harder one. Talking about the bound import information, again, it's in the data directory. There's this entry points at these data structures that have time date stamps and offsets to names. And it looks like that. For purposes of the question, if you see something that has forwarder refs, subtract that many entries from how many bound import descriptor entries it has. And yeah, so I guess what I didn't cover before we broke for lunch, or broke for break, is the question is, like, how do you actually bind something, right? So if you want to go bind your binary, how do you do it? Well, there's an API, the bind imagex. The installer does have actually a bind image option that you can actually set something to bind at install time, so that, it's like if you're doing a new Windows install, you set it up to install, and then it binds it, and then it does this speed hack a little bit. There used to be a bind.exe, and this is not there anymore, starting certainly with the 2008 edition. I'm not sure if it was in earlier. But basically, it seems like they're not really providing bind anymore because they don't necessarily want you to still do it, even though they clearly themselves are still doing it. But how I did bind for these template binaries that you're going to deal with in the class is just one of these nice little things about CFF Explorer. You can throw any binary in there, go to the rebuilder, click the bind import table, and then CFF Explorer will go out and run around and say, okay, well, I see that this guy imports, okay, so that's a good example. Let's do this just for the sake of it. All right, we said this is doing normal imports right now. The giveaway is kind of there's zeros here instead of negative ones. Right? If I click on one of these entries, that looks like an RVA. That doesn't look like an absolute virtual address, right? RVAs, not absolute virtual addresses. If I do rebuilder, click bind import table, rebuild, go back to the imports, and now that looks a little more like an absolute virtual address, but a little more clear down here. These are larger numbers. These are not. That doesn't entirely look right either. They're bigger than they were before, but they don't strike me still as absolute virtual addresses. Yeah, those are too far apart. That's just wrong. I think that one just didn't work. Let's try this. Or maybe if I don't click that. No, it's just like failing. All right, well, it's possible. It didn't work this time, but it did work on my template things. So I guess I can just show you, like, this is template 32.
Does that actually change the DLL, or is it just the data that you're looking at?
It only changes the data you're looking at, and then if you, like, say save, then it'll write it back out to the file. Yeah, so template 32, let me try it with this then. No, let me open. So, I mean, the only difference between these files that'll be read in the next round is that template 32 versus template 32 bound, for instance, is I just literally used CFF Explorer to bind it. So over here, import directory, kernel 2596, and over here, import directory, kernel. There we go. That looks more like an absolute virtual address, right? I'm not quite sure why it failed on the binding. I'm going to try it one more time without writing it out, so I don't break things. And let's try it. Oh, all right. I don't know. Having some bug right there. Not sure why that worked for me before, and it's not now. Moves without saving. All right. Anyways, moving along. As I was kind of already saying, ALSR and binding are kind of in opposition to each other. Binding makes the assumption that you're going to load this thing at a particular base address. ALSR moves the thing around. Now, that said, it's not entirely invalidates the things, right? So if NTOS kernel, or sorry, if kernel32.dll says I want address 760000, and the OS loads it at 770000, right? The OS loader could still fix up all of those bound imports by just adding the offset between where the ALSR'd it and where it actually ended up. So it doesn't have to necessarily recalculate everything. It could just add the offset to all those pre-filled in entries. So they're somewhat at odds. It can, I don't know, I should say, I don't know if it actually does that or not. So that's probably something I should find out. But basically, ALSR decreases the efficacy of this speed hack.